So in this video, we're going to talk about how to describe stretches and compressions of linear functions. So in a family of functions, the most basic function is called the parent function. The parent function of linear functions is f of x equals x, which is a line with a slope of 1 and a y-intercept of 0, 0. So all other linear functions are considered to be transformations of the parent function, and there are three types of transformations. In this video, we're going to be talking about stretches or compressions. A stretch or a compression will change the steepness of the graph of a line. So if we look at this picture here, in blue we can see we have the original parent function f of x equals x. In red, we have g of x equals 3x, which is more steep than the original function. In purple, we have k of x equals 1/2 x, which is less steep than the original function. So a stretch or a compression will change the steepness of a linear function. So a vertical stretch or compression takes f of x and transforms it to c times f of x. If the absolute value of c is greater than 1, the graph will be stretched vertically, which means it'll become more steep. If the absolute value of c is between 0 and 1, the graph will be compressed vertically, so it'll become less steep. So you can remember that the slope is what tells us the steepness of a line. So if a line is going to be more steep, that means that the value of m, which is the slope, is going to be bigger. If a line becomes less steep, that means that the value of m, which is slope, is going to be smaller. So just to give you a picture of what vertical compressions and stretches looks like, let's look at these three frogs. So the original frog is in the middle. If it's vertically compressed, you can see it becomes flatter. If it's vertically stretched, you can see the frog is like pulled up and down in the vertical direction. So what happens when f of x equals x is transformed to g of x equals 4f of x? So in this case, we have this value c, so c equals 4, so we have a vertical stretch. So a vertical stretch tells us that it will become more steep. So let's look at the equations to see if this is in fact true. So if I write the equation of g of x equals 4 times f of x. So I'm going to plug in the definition of f of x, which is x. So I have 4x. So if we graph these two on a line, we have f of x equals x, and then we have g of x equals 4x. You can see that g of x is in fact more steep than the original graph, which is in green. And if we compare the slopes of these two lines, notice that f of x has a slope of 1, g of x has a slope of 4, so the m is actually bigger, which is why the line is more steep. So what happens when f of x equals x is transformed to g of x equals 1/8 f of x? So 1/8 is the value of c, and then c is between 0 and 1. So that means that this graph is vertically compressed. So if it's vertically compressed, that means that it is going to be less steep. So let's write out the equation to see if this is true. So when we write out the equation, we get g of x equals 1/8 times x. So you can see here, 1/8 is the value of m, and then in the original function, the value of m is 1. So m is smaller, so that is why the graph is less steep. If we compare the two graphs, we can see that in green, we have f of x equals x, and then the graph of g of x in blue is actually, in fact, less steep. So if we have a horizontal stretch or compression, f of x will be transformed to f of kx. If the absolute value of k is bigger than 1, the graph will be compressed horizontally, so it'll become more steep. If 0 is less than the absolute value of k, and the absolute value of k is less than 1, the graph will be stretched horizontally, so it'll become less steep. It's kind of the opposite of what you might think it might be, because if it's compressed horizontally, it's going to be more steep, but if it's stretched horizontally, it's going to become less steep. And I'm going to show you what horizontal compression and stretches look like, just so you can make sense of this. So we have the original frog. If it's horizontally compressed, you see the frog becomes narrower. If it's horizontally stretched, you can see the frog becomes wider. So that's why we have this idea. If it's compressed horizontally, it becomes more steep, and if it's stretched horizontally, it becomes less steep. So what happens when f of x equals 2x plus 1 is transformed to g of x equals f of 2x? So in this case, we have k is greater than 1, so it is going to be horizontally compressed. Okay, so that means that the graph is going to become more steep. So let's plug this in to see if it's true. So when we plug in, we get g of x equals, and then I'm going to plug in 2x to my input value. So I have 2 times 2x plus 1. So that gives me 4x plus 1. So you can see in g of x, my value of m is 4. And then in my original function, my value of m is 2. So m is bigger, so that is why my graph will be more steep. If I graph both equations, I can see that this is in fact true. So f of x is in red, g of x is in blue, and you can see that g of x is in fact more steep. So what happens when f of x equals 3x plus 2 is transformed to g of x equals f of 1/3 x? So 1/3 is my value of k, so which is between 0 and 1. So that means that my graph will be horizontally stretched. So it is horizontally stretched, so that means that my graph will become less steep because it's pulled wider in the horizontal direction. If I plug in to see the equation, I get g of x equals, and then I plug in 1/3 for x, and I get 1/3 at 3 times 1/3 x plus 2. 3 times 1/3, the 3 and 3 will cancel, leaving me with just x. So I have x plus 2. If I look at the slope of this line, the slope will be 1. That is the value of m. And then if I look at this original equation, my value of m is 3. So m is smaller, so that is why my graph will be in fact less steep. So if we look at the graphs of both lines, you can see here in green, I have the original graph, which is f of x. And you can see I have g of x, which is in fact less steep than the original graph, right? Because the slope is going to be smaller. So let's write the equation of the function g and describe the transformation between function f and function g. So we have 4 times f of x. I know that this is going to be a vertical stretch, but let's just write the equation and look at the graph to make sure. So I have g of x equals 4 times f of x, which is x plus 1. I can distribute the 4, so I get 4x plus 4. So if I compare 4x plus 4 and x plus 1, my value of m is going to be bigger. So that means my vertical stretch is telling me that this graph will be more steep. If we look at the graphs of both lines, you can see that the original is in red, and then the transformed function g of x is in blue, and that is in fact more steep than the original graph. Let's write the equation of the function g and describe the transformation between f and g. We have f of x equals 2x minus 1, and then f of 3x. So in this case, we have a c that's bigger than 1, so that will be a horizontal compression. So a horizontal compression tells us that the graph will be more steep. Let's look at the equations to verify that's true. So I'm going to go to g of x, and then I'm going to plug in 3x into 2x minus 1. So I have 2 times 3x minus 1. 2 times 3x gives me 6x. So I have 6x minus 1, which is my g of x. So if we look at the values of m, you can see that m here is 6. The original m was 2, so that is why my graph should be more steep. If we graph both functions, you can see that in fact, f of x, which is in red, is actually not as steep as the transformed function g of x, which is more steep. So the blue function, which is the transformed function, is more steep than the original. So in summary, when f of x becomes c times f of x, there is a vertical stretch when the absolute value of c is bigger than 1. There is a vertical compression when the absolute value of c is between 0 and 1. When f of x becomes f of k times x, there is a horizontal compression when the absolute value of k is bigger than 1, and a horizontal stretch when the absolute value of k is between 0 and 1.